clarify before you guys start asking questions is on the whole cuckoo thing. I don't think I did a great job of the second half of the cuckoo thing. So cuckoos basically, they reject eggs. But not everybody rejects eggs perfectly, and so there's some cost to rejecting the wrong egg. And the cost of rejecting the wrong egg.
I thought cuckoos were the ones that were putting their eggs.
Oh, I'm sorry. You're right. Sorry, my mistake. Cuckoos are the ones that put the eggs in. The host of the cuckoo rejects the eggs, but this is an imperfect rejection. The end result of that imperfect rejection is that sometimes you reject your own egg, you leave the cuckoo there in place, and as a result, the cuckoo then ejects all the other eggs when it hatches out. So there's this figure in your book where it has a thing like this: parasitism, you're not parasitized, or you're parasitized by a cuckoo, and then the host either doesn't reject or rejects the egg. And if you assume that these host birds have 4 eggs, if you're not parasitized and you don't reject the egg, then you get all 4 of your eggs. If you're parasitized and you don't reject, the nest parasite kicks out all of your offspring and you get nothing out of the deal. If you're not parasitized and you reject an egg because you think you might be parasitized, you eject 1 egg, but all of the rest of your eggs are fine. But if you are parasitized and reject the egg, the rejection is imperfect. And in about 70% of the time, you reject the correct egg. The brood parasite's already rejected 1 of the eggs, so you're already down to 3. Then you reject the brood parasite's egg, so you're still down to 3. But in 30% of the cases, 30% of the cases, which would be 0.3, you reject the wrong egg, and then the brood parasite emerges and boots the rest of your eggs out. And so this ends up being an average of 2.1. So because of this, even if you mistakenly reject one of your own eggs, having a habit of rejection is still better than just adopting the tendency to not reject eggs at all. And that's because even though you make a mistake and sometimes reject the wrong egg, rejecting is still better in most cases than not rejecting. So what this does to the host is hosts imprint on eggs. When they lay their first batch of eggs, they look at the eggs and they see the eggs and they're like, "Ooh, those are spotted eggs, those are my eggs." That then helps them notice if there's an egg that doesn't look like those eggs in the future, so it can boot it out because that's a cuckoo egg. So the question that your book asks is, why do hosts not reject offspring? Because oftentimes it's obvious to any observer that that chick is not a host chick. That's a cuckoo chick. It's 3 times bigger than the parent. Sometimes the parent is having to hover in front of the chick to stuff food down the gullet. Well, hosts imprint on eggs when they're first laid. If hosts imprint on chicks, what is the consequence of that? So we know, there are pictures in the book, we know that some of the chicks look like the host chicks. They actually are mimicking not only the eggs, but they're also mimicking the host chicks. If a host imprints on a chick, it's the first chick that you see. If the host is parasitized, it imprints on a cuckoo chick. And so for the rest of its life, it doesn't view its own progeny, its own offspring, as its own. It only is looking for a cuckoo chick. And as a result, all future reproduction is doomed. And so this then represents strong selection against the tendency to imprint upon the chick. Because if the first chick that you see is your own, then you imprint upon that chick. And then you'll accept all of your later chicks, but the cost of mistakenly imprinting on a cuckoo chick, especially because if you're parasitized, that's the only chick that's going to be in your nest. You now then reject all of your future offspring because they don't look like the cuckoo chick. And so there's strong selection to imprint on eggs, and there's strong selection to not imprint on chicks. Therefore, if there's a chick in your nest, you just feed it because you assume that it is yours. I think this is even clearer than the way I went through it with you in my office. And it's much more clear than the way I went through it in class. Does that make sense, Mason? Mm-hmm. Okay. All right. So I just wanted, as I was thinking through the test yesterday, as I was making the test out, it's done, by the way. I was like, I didn't do the greatest job of explaining that, and I could do better. So hopefully that clarifies, both for you in the room and any of you tuning in from home. All right, what questions do you have?
One of the questions I had was the equation for the game theory.
Oh yeah.
I was kind of confused what the actual equation was, and the hawk half, is it half V plus half C?
Yeah, so let's just go through the whole thing. Because I think students and professors, quite frankly, find game theory confusing and hard to work with a little bit. So game theory, first and foremost, has a set of rules associated with it. Some of those rules are rules about the interaction, and some of those rules are about the payoffs. So in this particular set of contests, the victor gets, what was it, plus 50. The loser gets nothing. But when a hawk is going up against another hawk, there's the possibility for injury. So there's a cost due to injury, and that cost is minus 100. And these could be units of energy, for example. But I'm not sure what the units are on the example that they use in the book. But it's basically just what do you get from engaging in the contest, what do you potentially lose in terms of gaining the contest, and are there any costs associated with being in the contest? So you have the aggressor, the individual that is initiating the interaction, and the aggressor can either adopt the strategy of hawk or the strategy of dove, and when it comes up against opponents, the opponents can adopt the strategy of either hawk or dove. And so this payoff matrix shows you kind of what the outcomes are, which leads to the next set of rules, which is that when hawk comes up against hawk, you win half the time, and half the time you incur an injury. Because you have two hawks going at it. If a hawk meets a dove, the dove runs away, which means that it gets nothing out of the interaction, but it also means that it doesn't incur any injury, and the hawk wins, because he's uncontested, essentially. And then when dove meets dove, because doves are doves, they share the reward. What this means is that when doves meet doves, each dove gets half of the reward, which is V. When hawk meets hawk, half the time they get the reward, and half the time they suffer the cost. When hawk meets dove, the hawk gets everything, and the dove gets nothing. And they don't even put the dove in the box in your book, but it's good to think that there is a dove involved in this. And then when dove meets hawk, the dove gets nothing because it runs away. And it gets no reward, but it also incurs no injury. So the question is, under these conditions, we put V in place, and we put 50 plus 50 in place of V. We put minus 100 in place of the cost. This is plus 25 minus 50, which gives you a reward for hawk on hawk of minus 25. The reward for hawk when it meets a dove is 50. The reward for dove when it meets hawk is 0. And the reward for dove when it meets dove is half of 50, which is plus 25. So it's not clear which of these strategies is an evolutionarily stable strategy. A strategy that if it's present in the population and everyone plays hawk, for example, dove can't come in. But if everybody is playing hawk, then all of your interactions come with a loss of whatever this is, of minus 25. So a single dove can come in, and even though the dove is going to be getting 0, it's not getting any deficit. And so a population full of hawks can be invaded by a dove. In the same way, a population full of doves is great, because doves are always beating doves. They get 25. That's awesome. But a single hawk coming in changes the game such that that strategy gets 50, which is more than dove, so selection would lead to an increase in hawks. So hawk does well in a population of doves. A single hawk, and a single dove does well in a population of hawks. And this is what your book means when they talk about an evolutionarily stable strategy being invaded or not. A population of hawks can be invaded by a dove. A population of doves can be invaded by a hawk. So clearly, one of these strategies isn't superior to the other strategy. So then the question is, what is the ratio of these two strategies that you would see out in nature based on this payoff matrix? And the way that you do that is you set, this is how your book does it. If H is the proportion of the population of hawks, that means 1 minus H is the proportion of the population that is dove. Well, then we can calculate what the ratio of these two strategies is going to be. So if we want to know the average reward to hawks, it's equal to the proportion of hawks in the population multiplied times the reward when hawk meets hawk plus the reward when hawk meets dove versus the proportion of doves. Okay? And in the same way, we can look at the average payoff of the doves for hawk times the reward to doves when they meet hawk, plus the proportion of doves times the reward when doves meet other doves. So this is the average payoff in a mixture of hawks and doves in this population. So the way we then solve for equilibrium is where the average payoff to the hawk is the same as the average payoff to the dove. So we just set these things equal to one another. So get these all distributed. That's just 0. So this would be 25 minus 25h. Let's add things together over here. So that's minus 75h plus 50 equals 25 minus 25h Let's make things positive. That gives us 50 equals 25 plus 50h minus 25 minus 25. We're working to get h by itself on one side. That's 50h equals 25 divided by 50 divided by 50. And we get h is 25 divided by 50, which is 1/2. So in this case, the stable solution, the solution at which hawk and dove settles into a pattern, is a population that is filled with half hawks and half doves. And that might mean that half the population is always playing hawk or half the population is always playing dove, but it could also just mean that each individual half the time plays hawk and half the time plays dove. It has the same effect. Now, if we change the payoff matrix, let's say that the cost of injury is not minus 100, but is instead minus 50. So the cost of interacting with a hawk is different. What that means is that half the time, the hawk will get the reward, plus half the time they will incur the cost of injury. Half of 50 is 25, and half of minus 50 is minus 25. So in that, well, it's gone now, but in that hawk versus hawk, that's now 0 rather than minus 25. Well, what does that do to this equation? Well, what that does to this equation is it takes this minus 25 to 0, which takes that out of the equation, which means that this is now minus 50 plus 50. And so we can recalculate from here on plus 50 plus 50. This is then 50 equals 25 plus 25h.
Wait, wouldn't it still be, it would still be a positive 15 that side.
What now?
Did you subtract 50?
So this is a minus 50 over here. Wait a minute. Oh no, sorry. I did that wrong, didn't I? Okay. So this is now, that's a plus 50. Oh, so that's minus 50h. Minus 50h plus
I think you just have two lines of the same thing.
50. I do. Yeah, I do. So this would be minus, wait, that's not right. Let's go back to the top. This goes to 0. This is 50 minus 50h. This is 25 minus 25. Right?
Yes.
Right. Okay. So plus 50h plus 50h is plus 25h. 25 is 50 over here. Minus 25 minus 25. So it would be 25 equals 25h. 25 divided by 25, h equals 1. At this point now, hawk is an evolutionarily stable strategy. It calls for a population of nothing but hawks. This then represents an evolutionary game where dove doesn't have a chance. So that heavy cost of injury to hawks, as soon as you reduce that cost, cut it in half basically, then that makes it impossible for the dove strategy to take hold in this population. So what game theory does for us is it helps us kind of think about what the different aspects of behaviors are. What are the rewards? What are the benefits and losses of engaging in a particular activity? What are the costs involved in engaging in those activities? And it helps us, after we figure out what it is for one situation, we can play with it and figure out what it would be for other situations as well. And so we can say, well, cost actually is really important because it takes a game, you reduce the cost by half, it takes a game that is a mixed evolutionarily stable strategy with 50% hawks and 50% doves and converts that game into a game that is nothing but hawks. Now you can't change all things. When dove meets dove, we calculated the gains as half of what you get if you win a competition. It's hard to imagine that going up because you have two individuals competing for a resource. The only way that that could go up is if it goes up for one of the doves and not the other dove, in which case that first dove is actually kind of now a hawk in a sense. And so there are some things that you can manipulate in the game, and then there are other things that you can't manipulate. This happens to be one of the things that would be harder to envision a practical scenario where you actually change that. What else? Does that help? That whole thing?
Can we just do like an overview, like we did last time, of like the main big topics, I guess?
Yeah. So we had finished up at the end of what we covered on the last test. We had finished up with those introductory chapters talking about animal behavior as a field and things like that. And so this information basically covers two chapters, I think, if I'm recalling correctly, which is the chapter on economic decisions and the chapter on predator-prey interactions. So one of the first things that we talked about when we talked about economic decisions was we talked about currencies, the currencies that you can use to basically analyze economic decisions. What are some currencies that we use in animal behavior? So energy is a good one. That's a good one to go to first. You know, whenever we calculate the net rate of energy gain, for example, in looking at a marginal value theorem for a forager, what other currencies could we have? Time. The less time you spend on something, the more time you have for doing other things. So you can think of organisms as being time minimizers. Trying to do things quickly, devote less time to one activity so that you can devote more time to other activities. What else? You guys read a paper about this. I'm not thinking food. Mating success. How many fertilizations do you achieve? In this case, per unit time. So in this case, you can actually think of two currencies that are involved. One currency being the number of matings, the number of fertilizations, but also that's also factored into time. So in this case, the currency wouldn't be matings or time by itself, but it would actually be the rate at which you achieve fertilizations. So you can also have currencies that are rates, number of fertilizations per unit time. Once again, you would be trying to maximize that rate, the number of fertilizations per unit time. And remember that when you have, this was gain, and what the gain was in this particular paper with the butterflies, the gain was number of fertilizations, and time was on the x-axis. So at any point on this curve, at this point, it's a certain gain per time. And so an individual should be acting to maximize that rate of gain per time. Well, the maximum is, of course, right here at the very beginning. But there's always some travel time involved And so you maximize your gain by factoring in travel time. And this is where the marginal value theorem comes into play. So the discussion of currencies went right into a discussion of the marginal value theorem. We talked about dung flies. We talked about a lot of other things, but we read a paper about dung flies.
So is diminishing return curve like the actual like the plateau right there, and then like the marginal value theorem is how long I have to spend? Like,
So
compounding?
yeah, so the marginal value theorem is just a way of predicting what will happen in terms of when an individual actually gives up the GUT, the giving up time. And the reason that it's called the marginal value theorem is within a given habitat, within the given environment of an organism, in some cases the gain curve will be high, some cases the gain curve will be low. The marginal value, this comes from accounting, where you calculate values in the margin. So if you're doing a spreadsheet of economic data, a bank account or something like that, you would have costs going out and income coming in, and the balance between those two things is in the margin. It's the far right or far left column in an accounting spreadsheet. And so what this marginal value is the habitat average. So this line that was in the paper that you read is actually an average across, in theory, all the cow patties that are available out there in the environment. When they get that average diminishing returns curve, that's when they then calculate, well, how long should one stay? And because organisms are simple, relatively simple, they don't develop a diminishing returns curve in their head for each cow patty that they tend to, but they have a general idea of what cow patties are like in general. And so what we generally see is we see that their behavior tends to converge on this average value. That's where the marginal value part of the idea comes from. Did that answer your question or not?
Yes.
Okay, all right, good. Sometimes I get partway through the answer, I'm like, was that the question that was actually asked or not? What else? Oh, yeah, you were asking about, the question goes on. Emily's sitting there looking at me like, are you gonna say anything more? Yeah, I am gonna say anything more. So the marginal value theorem was one of these economic models where we think about diminishing return curves and what that means for whatever the gains are. And the gains could be any of these currencies. We also then talked about the ideal free distribution and how that operates. And we also talked about models of prey choice. How do you choose what to eat based on the profitability of a particular prey item? And profitability, remember, was defined by the amount of energy that you get from a prey item divided by the handling time. And then we also incorporated the cost of searching for new food to decide whether you're going to eat prey 1 or whether you're going to eat prey 2. And those decisions about whether you eat prey 1 or prey 2 has everything to do with their profitability. And your book does a pretty good job of going through that. I worked through the math of that. They show you the answer at the end, but I actually showed you in class the math of how they got to that answer in figuring this out. So there was that. Then we talked about condition-dependent behavior. Because the economics of the choices that are available to you might depend upon what type of condition you happen to be in. If you are working off of a food deficit and you're on the verge of starvation, foraging in one habitat versus another habitat may be a different decision than if you have plenty of metabolic stores stored up in fat deposits and things like that. And we worked through a model that was in your book that kind of illustrated how that works. You forage in one habitat that has a low return, but it's a constant return, versus foraging in a variable habitat that sometimes gives you nothing, but sometimes gives you twice as much as the other habitat does. Well, it depends on whether you need 2 units of energy or 1 unit of energy. If you need 2 units of energy, you risk the riskier trade-off, because half the time you're going to stumble into the patch that has twice the energy, but having a patch that gives you 1 unit of energy doesn't get you across the threshold to make it to the next day if you actually need 2 units of energy to get there. And so we talked about that, and then that led into a discussion of kind of variability, wherein we talked about these studies done with woodpeckers, where the researchers had taken logs and drilled a bunch of holes in them, and then in some cases they put a single prey item in each hole. In some of them they put no items in any of the holes. In other ones they put 6 prey items in each, they put prey items in 6 of the 24 holes, and in another one they put it in 12 of the 24 holes. And then they looked to see how many looks into these holes birds would engage in, and whether or not the saturation of the holes in the log would actually affect that. And of course what they showed was that birds responded very quickly to changes in the saturation in those holes. If the choices of the logs were 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If the choices were an empty log versus a log where there's something in every hole, what did the birds do? Hmm? Well, they spent fewer looks. You look in a log and there's nothing there, guess what? I'm moving on. I'm moving on because I have experience that shows me if there's not something in one of these, there's not something in all of them. If I poke my beak into one hole and there's a prey item in there, what does that tell me? The Golden Corral is open for business. If, on the other hand, half of them are empty, and you come and you poke your hole in an empty one, it could be that the whole log is empty, or it could be that the whole log has stuff in there and you haven't stumbled across it yet. If you're here, you go poke, 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 poke. There comes a point where you begin to think, okay, this is just an empty log. I need to leave this and go someplace else. As opposed to here, if I go poke once, I want to poke again because maybe this is a log that has something, and then I stumble into one and I'm like, this is one of the logs that has prey in it. Reduce that to 1, 2, 3, 4, 5, 6. Now there's only 1, 2, 3, 4, 5, 6 holes with prey inside of them. Are birds going to poke their heads in more holes or less holes in this scenario compared to the other scenario?
More holes.
Yeah. So if we were going to rank these, so scenario 1 was a log with 0 prey versus 24 prey. Scenario 2 is 0 versus 12 prey. And scenario 3 is 0 versus 6 prey. Which one do you poke your hole? And you think of these things as looks. An animal looks into the hole. How many looks do you get in each of these ranked from most looks to fewest looks?
Most looks would be the 6. Fewest would be the 24.
So you can qualitatively rank these in terms of how many looks a woodpecker will put into these logs. And then I think that was the end of economic ideas applied to behavioral decision making. Is that correct? So we talked about predator-prey interactions. We talked about predator sequence. So that chart that I think is a really good way of thinking about how predation proceeds and what predators do to get prey and what prey try to do to get away from becoming prey. We talked about predator-prey arms race. And we talked about the snake-newt system, which was a review of stuff that you got back when you were first-year students. But we also then talked about other predator-prey arms races, the main one being the one that I began with today, which was the cuckoos and hosts. And the last one we covered were bats and moths and other insects in terms of echolocation and then strategies to avoid echolocation. One of these strategies is an active strategy of kind of jamming the sonar of the bats. And then we talked more generally about things like crypsis, mimicry, aposematism, and I think that covers everything in predator-prey interactions. And then the last thing that we were talking about was competition. I asked you to think about competition in terms of who is competing, what are they competing for, and we revisited some of these models of that were in the economic decisions, applying economics to things. We reviewed some of these in the context of talking about competition. So we revisited, for example, the ideal free distribution. What else? I didn't bring my book. What else was in this section? Oh, we just talked about game theory. I'm losing my mind. We talked about game theory as a way to think about competition, and we also talked about things like behaviors like scroungers versus producers and how that operates. Is there anything else in that chapter? We're not done with that chapter, so anything in the chapter that we haven't gotten to yet, it's not going to be on the test, obviously. Test 2 on the board. If I recall everything. Does this all sound familiar to you? No computer movements, just me. What else? There's bird foraging. I thought it might have been a nuthatch, which is one of these species that digs into the nooks and crannies on trees, kind of like a cavity feeding woodpecker. What else? My advice is things that have math in them, just practice the math a little bit and play with math like I encourage you to do with the game theory thing. You know, change the values and see what that does so that you get an intuitive sense of, well, what happens if the reward for hawks goes up? Well, probably that shifts it to favor hawks. What happens if the cost goes up for hawks? Well, that shifts it towards doves. What happens if the costs go down? Well, we saw that shifted it towards hawks. What happens if somehow magically the reward for doves goes up? It could be a situation, you could envision a situation where hawks and doves, when they meet, both get something out of the deal because hawks are not particularly hawkish or doves are not particularly dovish. such that there's a reward for both hawks and doves when doves go up against hawks. And then you can also then incorporate, well, in the process of the dove getting a little something, what's the cost of injury? So there are lots of ways in which you can play with that scenario, but playing with the game in general gives you an intuitive feel for how the game works. I also used an example in class, the prisoner's dilemma, which usually favors the police because they keep the prisoners in the dark. They offer an incentive for one prisoner to roll on another prisoner, and what usually happens is both prisoners roll on one another. And I also said, that's the way it normally works, but one way in which it doesn't work that way is in crime families where there's the possibility of retribution after the fact, and also you have tighter familial bonds between individuals, which makes them less likely to roll on one another, and then that changes, you basically change the rules of the game, and then that changes the outcome, which is why it's very hard to put mobsters in jail, because oftentimes they're family enterprises. So the game theory still operates what happens with mob families, rather than just me and Emily deciding that we're going to knock over a bank, is that we don't have a connection that makes her faithful to me or me faithful to her. I'm way more likely to roll over it on Emily than I am to roll over on my sister or my father or something like that. That changes the rules of the game, which then changes the outcome of the game. What else? Mason? All right. Same format as last time. All right. I expect to see some A's this time. Got nothing but B's last time. I expect to see some A's this time. Don't look at me that way.
Extra credits.
You guys are all capable.